Hello everyone, my name is Oğuz Khan. In this tutorial, I will talk about metabolism and transport module. We will first review the midazolam example project that we will be using in this tutorial. Then, we will apply an enzyme to midazolam project by using metabolism and transport module, and I will give detailed information about metabolism section. Thereafter, we will finalize the tutorial with the application of a transporter to midazolam project, with the focus on the transport section of metabolism and transport module. Before getting into GastroPlus, I would like to give brief information about midazolam. Midazolam is almost completely absorbed when it is administered as solution. However, its final bioavailability is 25 to 30%. This is because of the high first-pass elimination in both gut and liver through CYP3A4. In the following part of this tutorial, we will assign CYP3A4 as a metabolizing enzyme of midazolam. The in vitro data that we are going to use for the enzyme kinetics are summarized in this table with its respective reference. Currently, we are in the midazolam example project that we will use in this tutorial. The example project has already been fully set up except for enzymes and transporters. If we navigate to compounds view, we only have one compound which named as midazolam. In the enzyme kinetics panel, we can see that there is no assigned enzyme for this compound. In the dosing view, under the formulations panel, we have two different formulations, intravenous bolus and per-oral solution. In the dosing schedules, we have four different dosing schedules, one for IV bolus and three for per-oral solution. In the physiologies view, we have created one physiology as human American male, healthy, 25 years old and 70 kg, based on the study population of the experiment. In the pharmacokinetics view, we have assigned blood-plasma concentration ratio, experimental fraction unbound in plasma based on the literature findings. In the PBPK plus panel, we assumed all the tissues are perfusion limited, and elimination is only happening through the kidney filtration clearance for now. In the simulations view, we have four different simulations for four different administration. For this tutorial, we will keep going on with per-oral simulations. In order to run the per-oral simulations simultaneously, we will navigate to Runs view, select the batch simulations run that has already been created, and add our three oral simulations. Then we will click on the Start button. Over here, we can see that the elimination of the simulated curves are under-predicted. This is because of the lack of the CYP3A4 enzyme. In the summary view, the predicted bioavailability is almost 100%, which is inconsistent with the findings in the clinical study. In order to assign CYP3A4, we will navigate to Compounds view. In the Compounds view, we will expand the enzyme kinetics and click Add button. Once we click on the Add button, a new row with default parameters are going to show up in this table. In this table, our first column is species column. In this column, we will choose the human, but users are able to choose non-human clinical species too. Based on the species that we are going to choose here, the enzyme will be linked to that species. In the enzyme part, we will choose CYP3A4, which is default. And for the phenotype, we will keep going on with the wild. However, we also support 5 different phenotypes. Based on the selection here, the enzyme expression level in the liver is going to be affected. In the location column, we will choose PBPK tissue. Then we will click on Add button again. We will select the enzyme as CYP3A4 one more time, but this time the location will be enterocytes. The reason for assigning a second row for enterocytes is that metabolism in the liver tissue is part of the PBPK model, while enterocytes are a component of the ACAT model. Metabolism in GastroPlus is handled separately for the PBPK and ACAT models. Therefore, if you are going to assign any enzyme that is occurring in PBPK tissue and the enterocytes at the same time, they need to be assigned in two different rows. Currently, we are done with editing the enzyme kinetics table, and we are ready for in vitro in vivo conversion of Vmax and Km through metabolism and transport module in the right-hand side of the screen. In the metabolism and transport module, first of all, we need to assign the combination of compound and physiology that the conversion is going to happen. For the tutorial, we will stay with midazolam and human 25 years old 70 kg combination. Then we need to define the assay and the in vitro fraction and bound in the experiment. For the assays, GastroPlus supports 5 different types of assays. Based on the selection here, the following panels will update themselves to adapt on the assay. For instance, currently we are in the liver microsomes. If I change the assay type to hepatocytes, the scaling factor will update itself for the scaling factors of hepatocytes. In the kinetic experiment that we are using, the assay type is indicated as liver microsomes. For the in vitro fraction and bound, GastroPlus provides 5 different options, including 2 options of prediction method from physicochemical properties of molecule. Based on the selection, the fraction field on the right will update itself to give information of what number are going to be used for the calculation. For example, if I select Austin method, the fraction part will update itself to this number. If I select user-defined, the fraction part will become editable and user can enter manual number here. In the experiment, the fraction unbound is given as 100%. Therefore, I will select is unbound. Scaling factor panel is a dynamic field that updates itself based on the assay type. This panel provides information for the scaling factor that are going to be used in the conversion. Users should edit the tissue based on the location of their enzyme or transporter of interest. For the other scaling factors, we do not suggest to change them unless you have a specific number for those parameters. For this tutorial, we will select the liver tissue since the experiment was conducted on the liver microsomes. In the metabolism panel, a table for enzymes will show up at the top. This table provides information about the enzyme of interest. If you assign 2 different enzymes into the enzyme kinetics table, you can select which enzyme you are going to do the conversion from the enzyme column. Once we selected the enzyme of the interest, GastroPlus have 2 different options to do the conversion: metabolic clearance and Michaelis-Menten kinetics. In some experiments, the result can be given as clearance. For these experiments, GastroPlus has an option of metabolic clearance conversion. In the metabolic clearance subpanel, users need to select the source and type of the results. For the source, GastroPlus provides 2 different options. For the type, GastroPlus provides 3 different types. Based on the selection here, the unit of the in vitro clearance will update itself. For in vitro, the unit will be per milligram protein. For tissue, the unit will be per gram tissue. For intrinsic, the unit will be per kilogram body weight. For now, we will keep going on with the in vitro, and we will assign in vitro clearance as 1 microliter per minute per milligram protein and hit enter. Once I hit the enter button, GastroPlus will automatically calculate unbound in vivo clearance right over here. If I click on this transfer button, this number will be transferred to the intrinsic clearance value for the liver in the PBPK model, as we have selected liver as a tissue in the scaling panel above. So let's observe this. Let's go to the PBPK Plus module in the right-hand side of the screen. And over here, we can see that the number is successfully transferred into the intrinsic clearance part of the liver. Since this is not the case for our experimental study, I will set this number to 0 and go back to metabolism and transport. The metabolic clearance panel also provides conversion from clearance to non-saturable Michaelis-Menten kinetics, with the Km input from user. For example, if I assign a Km value of 10 mg per liter and hit enter, GastroPlus will automatically calculate non-saturable Vmax and PBPK Vmax. The difference between these two Vmax values is based on location, where PBPK tissues use the unit of milligram per second milligram enzyme versus milligram per second in other locations. This allows the Vmax to scale the expression of the relevant enzyme in PBPK tissues that express the enzyme. In this way, if an enzyme occurs in 2 different tissues, it can be scaled into these tissues based on the expression level. If I click the transfer button, these numbers will be transferred to the enzyme kinetics panel in the compounds view. However, this is not our case, therefore I will not click on the button. In other experiments, the results may be given as Vmax and Km. which can be converted in the Michaelis Menten kinetics subpanel. In this subpanel, users need to define the Vmax type, which can be in vitro or intrinsic. Based on the selection here, the unit of the Vmax will update itself. Once users define the Vmax type, then they need to input the Vmax and Km numbers from the in vitro experiment. In the experiment that we are using, the Vmax was given as 0.85 nanomole per minute per milligram protein. The Km was given as 3.7 micromole per liter. Once the numbers are edited in the respective fields, the GastroPlus will automatically calculate in vivo Vmax and Km numbers. Note that GPX calculates two Vmax values, one for PBPK tissues and one for other tissues such as enterocytes. If you assign two or more different metabolites to enzyme indicated here, you can select which metabolite you are conducting the conversion in the metabolite dropdown. This does not impact the calculations, but it does affect which rows the in vivo Vmax and Km values are transferred to. Since we are not tracking any metabolites, we will keep going on with the none option here. If I click the transfer button, the in vivo numbers shown here will be transferred to the enzyme kinetics table in the compounds view. So I will click on the transfer button, and I will navigate to compounds view, expand the enzyme kinetics panel, and the numbers are successfully transferred to this place. GastroPlus also provides the option to convert in vitro Vmax and Km numbers to in vivo intrinsic clearance, which can be conducted in the bottom part of the subpanel. This is the opposite conversion of that shown in the metabolic clearance subpanel. Currently, we are done with in vitro in vivo conversion of Michaelis Menten kinetics, and we assign the CYP3A for metabolism directly from the literature. Now, let's observe the simulation results at this time. Before running the simulation simultaneously, I would like to point out the metabolism toggle in the simulations view. Under the compound settings, there is a toggle responsible for enabling and disabling metabolism. Be sure this toggle is enabled for the respective simulations. There is also the same toggle for the transport mechanism. Once you are sure about the metabolism toggle is enabled, navigate to Runs and run your simulations. Currently, we are going to run the same simulations as we run in the first time of this tutorial. I will click the Start button. As we can see in the results here, the simulated curves are fitting reasonably well if we consider direct implementation from the literature. If we navigate to Summary view, the bioavailabilities are in the correct range. We can also observe that bioavailability is increasing with the dose, which indicates saturation of CYP3A4 at higher doses. We can optimize the saturation of enzymes, but this is a subject for another tutorial. Currently, we are done with metabolism implementation. As a next step, I will demonstrate how to implement transporters. In order to add a transporter, we will navigate to Compounds view and expand the Transporter Kinetics panel. For the tutorial purposes, we will add OCT2 as a hypothetical transporter to this example. I will click on Add button, and I will choose OCT2 from the Transporter drop-down menu, and I will set the location for PBPK tissues. Before getting into Vmax and Km conversion, I would like to show where the transporter occurs in the PBPK tissues. I will navigate to PBPK Plus in the right side of the screen, and I will click on the kidney tissue. In the right side, I will find the transporter table. In this transporter table, we can get the details about transporters in this tissue, such as expression levels, flux types, and membrane locations. If I enable the toggle on the top right of this panel, it will filter the transporters based on the currently selected compound. For example, if I now click on the liver tissue, the transporter table will be empty since OCT2 does not express defaultly in the liver, and also the OCT2 is the only transporter that we have assigned for this compound. Now I will navigate back to Metabolism and Transporter module to start the conversion for OCT2. Currently, the assay is selected as liver microsomes. Since the transporter studies cannot be conducted on this assay type, I will change it to express cells, assuming our hypothetical transporter assay was conducted in HE key cells. Then, I will navigate to scaling factors and change the tissue to kidney. I will go to Transport panel. On top of this panel, we have similar table as we observed in the Metabolism panel. This table provides information about the transporter of interest. If you assign two different transporters to your compound, you can simply select which transporter you want to use from the transporter dropdown right here. The following part of this panel can do two types of conversion: Vmax and Km for active transport, and diffusional clearance for passive diffusion, which relates to PSDCs in GastroPlus. For the in vitro in vivo extrapolation for active transport, users need to define the Vmax type first. Based on the selection here, the unit of the Vmax will update itself. For this tutorial, I will assign a Vmax of 10 nanomole per minute per milligram protein and Km of 1 micromole per liter. Once I hit the enter button, the converted in vivo Vmax and Km will be calculated automatically. If I click the transfer button right over here, it will transfer the in vivo converted numbers to transporter kinetic table in compounds view. I will click on this button. I will navigate to compounds view, and here we can see that the numbers are successfully transferred here. I will navigate back to Metabolism and Transport module. One other thing that needs to be pointed out that GastroPlus also calculates active transport clearance from the Michaelis-Menten kinetics. But this number is only for information purposes and cannot be transferred. Before getting into diffusional clearance, I will set the numbers for Vmax and Km to 0. Then I will select the clearance type, which is going to affect the unit of the clearance. So my clearance type is protein, and I will assign the clearance the value of 10. Once I hit the enter button, the GastroPlus will automatically calculate unbound diffusional clearance and specific diffusional clearance. These are the numbers representing to passive diffusion in permeability limited tissues and can be transferred to PBPK Plus with the transfer button right over here. And this transfer will happen based on the information that we have given in the location and type part of right over here. Currently, we have demonstrated how to implement transporters into compounds. Be sure to check your tissue type and transporter toggle in the simulations view before running the simulation. Thank you for watching our tutorial. If you have any questions regarding to these tutorials, please reach out to us through these emails.